How are you all doing? Welcome back. We're going to be going over chapter 6 today. And last week, I apologize that it wasn't like a usual video like this. It was an older lecture I recorded last semester. And I just didn't have time to re-record a lecture. So this week we're going to be looking at atmospheric moisture, how we get rain, how we get those clouds in the sky, and looking at we're looking at the water cycle, right? The evaporation, condensation, precipitation, and runoff that happens within that water cycle, okay? So let's get started. So when we start every chapter, it usually, and if we were in the classroom setting, I would definitely be starting the lecture with this question: what's the impact of this on the landscape, right? How does moisture impact the landscape? Well, you can see that in very many different ways, right? So you can see that short-term and long-term. Short-term, when we're looking at puddles, streams, flash floods, you can definitely see that right away and how that happens. And long-term would be weathering and erosion. So like rivers will carve out, or water will carve out these canyons, right? Take tiny, tiny deposits of sand or gravel or whatever the case is, and over time you start to see the way erosion really shapes the landscape. So it's kind of two ways, right? It's short-term and long-term. Water is the most widespread substance on Earth, more than 70% of the surface area of the planet. So let's start with the hydrologic cycle, or the water cycle. You guys have learned this before, maybe like in grade school, 7th to 8th grade, maybe high school, right? It's just evaporation, and then condensation, and then precipitation. Really easy, right? So we're going to be looking at those different processes, and we're going to take time on each of those steps. So you have liquid water. It evaporates into the air, condenses into liquid or solid state, and returns to the earth as some form of precipitation. And here in California, all we're really used to, and if we're lucky, is that rainfall, right? We're lucky to see rainfall if we get rainfall. So let's look at it a little bit more in depth. So look at this picture here. Obviously, evaporation is going to happen over the oceans, correct? Because that's where like the big reservoir of water is, that ocean water. And then you have evaporation, you have water that turns into water vapor, right? And then that water vapor molecule will turn back into a water molecule, and then you have a cloud, okay? And so now you have winds which push those clouds over land. Then you have precipitation, right? It happens over land. And then most of that precipitation will make its way back into the ocean, right? You do have some of that water that goes underneath the ground, which is called groundwater. So when we look at things like what's happening today, and when, we have all these wildfires, and, people will argue and say, well, that was started by arson. There is no way that climate change, you can blame that on climate change. Yes, we know that that fire was started by arson, right? Whatever fire it is that we're talking about. We know it was man-made. But if it weren't for the conditions that we have because of climate change, that fire would be contained easily. Does that make sense? So because we are in a drought, meaning that there's not a lot of rainfall, and we're in a very dry area, so those two things add to the fuel aridity, which means that all that vegetation, because there's no moisture in the air, because it's dry, it sucks all the moisture out of that vegetation. Number two, because there's no snowpack up in the mountains, even far away from here, all that water that falls as snow, it freezes, and then during the spring it comes down and feeds all that vegetation and goes deep underneath the ground as groundwater. So not only in the winter do we have that water coming in, rainfall here in Southern California, snowfall in Northern California, but throughout the year, all that has fallen, all that snow that begins to melt, it feeds the entire, watershed of where that snowpack has been. And so now conditions are moist. But because of climate change, we have drier conditions, less moisture in the atmosphere, less moisture in the air, sucking moisture out from the vegetation, making it extra dry. We also have less snow. So when it rains, when precipitation does fall, it falls as rain. And guess what? There's no snowpack in the mountains. And now that snow cannot melt because there's no snow to melt and cannot feed the entire forest. And we have all these dead trees. So because there's no moisture, there's a lot more dead trees out in those forest areas, in those foothills, in the hills, in the mountains. Dead trees accelerate and burn very, very quickly. Dry vegetation burns very, very quickly. So when the governor says that climate change is to blame, he's not saying that it wasn't started by arson. What he means, or what we mean, what scientists mean by that, is that if conditions were normal, that human-made fire could have been easily contained. Does that make sense? So I don't want to get political here, and that's not what I'm here to talk about, but I want you guys to understand that yes, we know that fire was set by humans, but if it wasn't for climate change and our conditions being drier, where they're already dry, but extra dry, extra arid, and our conditions having less water in a drought, less snowpack, less groundwater, then that fire could have been quickly and easily contained. Okay? So I kind of went off on a tangent there, but I think that this is a very teachable moment, and that's important for you guys to understand, okay? Because there's a lot of things out there, and people will argue and say, or like the president will say that science doesn't know, right? This has been a long time coming. I mean, we've been looking at the way climate change will kind of put the hand on the throttle when it comes to wildfires. And now when we're in wildfire season with the Santa Ana winds, that offshore flow that we talked about last week, then that is just like all these other perfect conditions, unfortunately, to rage those wildfires. So they're not just really bad right now. I hate to say this, and I don't want to say this, but it's going to get worse because conditions are going to continue to get more dry. There's going to be less water available, less snowpack available, less snow melt available, and hopefully we continue to fight, because climate change really is the fight of our generation. Okay, so I spent a lot of time there, but that is a very teachable moment in what's going on today. So before we look at those steps, evaporation, condensation, precipitation, surface runoff, how clouds are made, what type of clouds, how does water get from the surface of the ocean or from the ocean to the atmosphere back down again? Well, water is a very important liquid. Water is very important. Why? Because it has several important properties that make water available and easily moving, and move easily from the surface of the earth to the atmosphere back down again. Okay, so number one, first important property of water obviously is water is liquid. Water is liquid, found at temperatures at most places on Earth's surface. The liquidity of water enhances its versatility as an active agent in the atmosphere, lithosphere, and biosphere. Number two, ice expansion. Obviously, when ice freezes, or when water freezes, is it heavier or lighter than water? It's less dense, right? It floats. How do we know? Because when we're drinking our margarita on the rocks, or maybe your soda, you know that ice floats to the top, right? Not unless you have like a pitcher of margaritas, can you really see the ice float? And you shouldn't be drinking margaritas out of a pitcher unless you have your friends with you, right? So we know that ice floats, and so that is another important property of water. Number 2, surface tension. Liquid molecules are sticky. Remember, you learned this a long time ago, right? You have H2O, and here are the molecules, right? And now this is a sticky situation. So that means that these molecules of water, they stick together. They're adhesive. So this gives water a high surface tension. So liquid molecules tend to stick together, giving water extremely high surface tension. It's almost like this thin skin of molecules form on the surface of water, causing it to bead. Some insects can use the stickiness of water and walk on top of water. So like mosquitoes, very, very tiny insects can use that adhesive property, that stickiness, that surface tension of water, right? And this doesn't look like water there, but that was H2O. Okay, let's go to the next slide, and we're still looking at the important properties of water. Capillarity, still thinking about that. Those molecules tend to stick together, right? They don't bounce away from each other, they adhere together. So capillarity, water molecules stick easily together and to many other surfaces or substances, a characteristic known as adhesion. Water can sometimes climb upwards for many centimeters or even meters in an action called capillarity. This enables water to circulate upward through rocks and cracks, soils and roots and stems. So how does water get from the soil, the bottom, all the way to that leaf? It's through the capillarity ability of water. Because it beads, it's able to climb upwards. If you have ever noticed when you are drinking, I kind of froze here. Okay, so when you're drinking your beverage, right, you have your water here, then you have your straw inside the water, or whatever liquid you're drinking, right? You notice that the water level might come up to here. Does that make sense? So instead of it being like right where that water ends, it climbs upwards. So next time you guys are drinking your chocolate milk at night, notice that. Or actually, you shouldn't notice that because we shouldn't be using straws anymore. We need to save the turtles, right? That's a whole nother lecture. Or maybe if you have a clear straw, reusable straw, you can notice that. The solventability of water. So water is known as the universal solvent. What does that mean? Water can dissolve almost any substance, and it is sometimes referred to as the universal solvent as water moves through the atmosphere, on the surface of Earth, and in soil, rocks, plants, and animals. It carries with it a remarkable diversity of dissolved minerals and nutrients. Specific heat. Water has a great heat capacity. We learned about this. We talked about this in chapter 4, right? It takes a lot of energy for water to heat up. Is that correct? Yeah, right? It takes a lot of energy for water to heat up. So water has a high specific heat. Okay, so we're going to get on to the visible component of water in our atmosphere, okay? So we're going to look at clouds. Clouds are collections of tiny, very tiny, minute droplets of liquid water or tiny crystals of ice. Not all clouds precipitate, but all precipitation comes from clouds, right? We know if we go outside right now and it is actually first day of spring, it's fall, sorry, and it's extra hot. That's why I have a tank top on. But if I were to go outside and I see a cloud, I'm not going to say, oh, there's a cloud, it's going to rain. No, we know that not all clouds bring rain. We can already tell what type of cloud is going to give us rain, just by common knowledge. Well, in today's lecture, you're going to notice and be able to name that type of cloud that you know for sure is going to bring in rain. So before we get into how clouds are created or how they form, we're going to look at different types of clouds, okay? So they are classified on two things, on how high they are up in the troposphere and the shape of the cloud, right? So you guys might have learned this a long time ago, cumulus, all those different shapes of clouds. We're just going to go over it really quickly. So clouds are classified on two things, on shape and on height. Okay, make sure you write that down. That is definitely going to be an exam question. So cloud shapes. It's going to be either cirrus, stratus, or cumulus. And then depending on how high they are in the atmosphere, then they're broken down into kind of like a mixture of different clouds. So you can have 10 different cloud types. But what I want you to worry about is these basic 3 cloud shapes, okay? First is a cirrus or cirriform clouds. These are wispy hair-like clouds, and they will look something like this, right? I mean, nothing close to that, because obviously I have the worst little marker here to draw, but it's like really wispy clouds, okay? So those are called cirrus clouds. That word is Latin for lock of hair because they look like thin, wispy locks of hair, and they are composed mostly of ice crystals rather than water droplets. Stratus clouds, these are low-hanging grayish sheets. You will notice that they rarely break into individual cloud units. So these are the clouds that you'll know that you're going to have rain because it's just like gray sky, right? They don't break up into like different clouds. It's just one low-hanging gray sheet. Cumulus clouds, these are the fun clouds that are easy to draw, right? Flat base. They can extend very, very high. These are the ones you can look in the sky and be like, oh, wow, did you see the elephant in the sky or bunny rabbit? I don't know. They're massive and rounded, usually with a flat base and limited horizontal extent, but billow upwards to great heights. Okay? So here we have cumulus, the one we talked about, cirrus, and stratus, right? And then you have a combination of different things going on here. So you have, depending on the height that they extend, they could be cumulonimbus clouds. These are going to give, it's like a tongue twister. Cumulonimbus, cumulonimbus, cumulonimbus. Try to say that 5 times fast. Cumulonimbus clouds, these are going to give you very torrential rain, and they're going to give you like thunder, lightning, things like that. They extend very, very, very high. Altostratus, so it's going to be higher stratus clouds. Stratocumulus, a combination of cumulus and stratus, kind of, right? Little puffy clouds here. Nimbostratus, definitely you're going to get rain from this nimbostratus clouds. And altocumulus, so you guys can look at all these different cloud types. I'm not going to, you're not going to be tested on every single cloud type on this slide, but know the 3 basic cloud shapes, okay, cloud types. And here we have cirrus clouds. So like if we were in a classroom, I'd say, what cloud do you guys think this is? And you guys would be like, cirrus. And I'd be like, yes, you guys are so smart. Oh my God. Yeah, this is some form of cirrus cloud, same cirrus. This is probably altocumulus, cumulus cloud, stratus, and nimbostratus for sure here. Okay. And then based on their height, right? You have high clouds, middle, low, vertical clouds, and then you have the type cirrus, stratus, cumulus, and you don't have to worry about this chart. It's just really how those 10 different cloud types, a little more than 10, get their specific name. Okay, so because we're talking about clouds, let's think about fog. That's something really exciting, right? If you live in California, I know I get excited when there's fog because there's nothing else really atmospheric wise to get excited about. And forget it, when it hails here in California, I freak out because that's really exciting. But when it comes to California, I think it's a blessing and a curse, right? It's cool that we don't get much action. We don't have tornadoes, hurricanes, things like that. So when it comes to fog, I get excited. Maybe it's just like the nerd in me, right? But if you've ever wondered what it feels like to touch a cloud, it's actually just fog. Isn't that kind of a letdown? Don't you wish that they really, really felt like cotton candy or something? But they don't. It just feels like fog. And when you know, if you've ever been through very thick fog, when you're in the thick of it, it kind of starts to disappear and it just, do you know what I mean? So fog, simply put, is a cloud on the ground. But there are different ways that fog is formed. Okay, so we're going to cover the 4 different ways. It's just a low level cloud and it's stable, so it's a low lying stratus cloud. That's really what it is. However, there's different processes that happen, and there's an exchange in heat, cold air and warm air, and that causes fog to happen, or it forms fog, if you will. So let's look at the different ways that fog forms. First way is, and I'll have pictures on the next slide so you guys can see exactly how it looks, okay? So radiation fog, when you have, like, you know, at nighttime, the ground is losing heat. All that heat that it has absorbed all day, it's losing all that heat, right, pretty quickly. So if you think of like a soccer field or even a cemetery or a large park, if you've ever driven by one during the morning or evening, you can see that there's fog over areas like this. Why? Because that land, that ground is losing heat at night. It's radiated away, and you have cold air that passes over like that park or the grave site, the graveyard or the cemetery or whatever those examples were that I gave you, right? And now that forms like a low-lying ground cloud on the ground. Pretty cool, right? Next type is advection fog. You have warm, moist air moving horizontally across a colder surface. So this wouldn't be like a soccer field or a park because those are losing heat at night, right? So this would be like a lake. A lake would be a colder surface, and it would be possible for warm air to move across it horizontally. So remember, think way back to chapter 4. We talked about all these heating and cooling processes, and I said anytime there is a horizontal movement of air, that is going to be advection. So we call this advection fog. Next type is upslope fog. So if you think back long time ago to our exam, and think of adiabatic cooling and adiabatic warming. So what happens when a parcel of air or warm air starts to rise? As it rises, it starts to get colder, right? And then it starts to condense up there, right? So that also can be applied to, say you have a mountain and you have like this warm air that hits this topographic barrier. It could be a mountain slope or a hill slope, and it's pushed up the side, and as that warm air rises, because warm air rises, it starts to condense and turn into, fog, right? If you've ever looked at the mountains on a very clear winter day and you see that those mountains are surrounded by clouds, I know you guys have seen this, that is adiabatic or upslope or orographic fog. Sorry, it's just orographic, upslope fog. And if you were there in those mountains, it would look like a cloud. Does that make sense? So that's like a perfect image. I see it all the time if you're driving on a clear winter day towards the mountains, like on the 605 even. It just, I know you guys have seen this picture before. So that's like a great example of what adiabatic fog looks like. It doesn't have to be mountains. It could be just a hill. It doesn't have to be that high. And evaporation fog, think of like when you take a shower, a hot shower, you're adding water vapor to cold air, you form a little cloud fog in there. That's like you're making your own little cloud inside the restroom. So here is your examples that I just went over. Here you have radiation fog, you have advection fog, upslope fog, or orographic fog, and then this would be evaporation fog. Okay? Because we are talking about clouds, I do want to take some time, and this is not in your book, but I think it's important to talk about this very unique and unfortunately threatened ecosystem. So these are called cloud forests. Cloud forests are characterized by persistent low-level clouds. They're not found everywhere in the world. They are threatened because of climate change. So in order for clouds to form and be low level and have it be a cloud forest, conditions need to be just so, right? There just needs to be enough cold air and warm air. Now, because our climate is changing, the location and the availability, or what's the word I'm looking for? The amount of cloud forest is getting smaller. It is a threatened ecosystem, and you will have a video to watch about a cloud forest in Mexico called El Triunfo. It is found in the forests of Chiapas, Mexico. So people are really amazed, not amazed, but maybe you are, maybe you're not, to see the diversity and the amount of different ecosystems found in Mexico. You know, obviously there's desert. There's also this like almost tropical rainforest. You have the beautiful beaches, which is also tropical, of the peninsula of Yucatan. You have deserts. You have Baja California, which is complete desert, completely different from the southern portions of Mexico. So it is very, very diverse. There's more to Mexico than narco corridos, glorification of gangsters. All this is a very bad rap that we have gotten, and unfortunately when people think of Mexico, they just think of these terrible things that we here in the United States perpetuate. So what do I mean by that? We enjoy watching things like Narcos Mexico. We think it's cool to glorify that lifestyle. We listen to things like narco corridos, which is glorifying the gangster, drug dealing, murderous lifestyle that is not at our cost, right? We don't experience any of that. Who experiences that violence? It's people on the other side of the border, these marginalized communities, people with no other choice, but it's glorified here. So if you guys are interested in that discussion a little bit more, there is a really good and extremely graphic documentary on Netflix. I think it's still on Netflix. It is called Narcolandia, and it just shows how we here in the United States, on the other side of the border, very, very close to this country of Mexico, perpetuate this lifestyle, right? It is glorified here in the United States, and it follows around this this group, this narco corrido group from Vernon, California, and sings about AK-47s and beheading people and cocaine and that entire lifestyle, and it's at the cost of real lives. And it's incredibly sobering and eye-opening. And I mean, trust me, I love watching Narcos Mexico. That was a great documentary. But we really have to sit back and analyze what is really happening, because lives are really being lost. You look at little girls in Sonora, Mexico, or Sinaloa, Mexico, sorry. You ask them, hey, what do you want to be when you grow up? 13-year-old girls. Can you believe that they say that they want to grow up to be a narco's wife? How sad is it that in this country they have no other aspiration, right? Because it's cool to them. So it's just something to think about, guys. I'm going off on a lot of tangents today, but I think that's good. Again, geography is not just physical, it's human and physical, and those two worlds definitely collide all the time, okay? So here are some places where you do find this cloud forest ecosystem. In Mexico, it's called El Triunfo. Costa Rica, Chile, Canada, parts of North Pacific United States, we do have cloud forests. Ecuador and Spain, high biodiversity. What does biodiversity mean? Biodiversity means that there's a lot of different plant species and animal species. It's high in biological diversity, lots of different kinds, okay? Here are some really cool animals from some of these cloud forests. This is called a spectacle bear from the Andean cloud forest. This is a sloth. How funny and cute, right? This is from Costa Rica. This here is a little fox. And I don't know what cloud forest it is, but I put it there because I love foxes. They're my favorite animal. And this is a quetzal. So here's just another picture of a cloud forest. Really cool ecosystems, guys. All right, so let's look at dew. Dew is very closely related to fog. You have kind of these two changes or these differences in temperature, right? Surfaces and air above it. So when you have nighttime objects, nighttime objects begin to cool, like your windshield or a flower or the grass outside, right? The air above that object is cooled by conduction. What does that mean? The air above your windshield, that flower, it's cooled by conduction. If the air is cold enough to saturate, then your beads start to collect on that surface of your windshield, of the grass, of the flower, of the spider web, whatever it is, right? Now, if temperatures dip to a certain point and they freeze, those beads, that dew, turns into frost. Pretty easy, right? Okay, so we're going to get into evaporation, then condensation, then precipitation. I kind of gave you the very beginning of chapter 6, and now we're going towards the end. We're getting to that water cycle step, the hydrologic cycle: evaporation, condensation, and precipitation. Okay, so let's look at evaporation. Evaporation is what puts water vapor into the atmosphere, right? So think of water vapor. Obviously, it's invisible. You can't see it, right? It's like gas molecules of water. Okay, water vapor is odorless, colorless, and tasteless. So even if the majority of water on Earth is liquid, we're going to try to understand the development of clouds and precipitation and condensation, evaporation, right? We're going to talk about water vapor because it's the source of moisture for clouds and precipitation. So let's look at the process that puts water vapor into the atmosphere. If I were to ask you guys, without knowing, how do we get water from the ocean to turn into water vapor? Yeah, right? We need some type of heat. So there needs to be that jiggling of molecules, if you remember back to chapter 4, right? Those molecules need to start to move and get that energy, bump into each other, and change their state from water to vapor, to gas, right? To water vapor. So we can see in this simple example here, even if there is no heat, for example, in this picture here, even if the burner is turned off on the stove, you're still going to have evaporation happen, right? Even with the burner off, some molecules break free from the surface as water vapor, and then some are just going to return from the air back to the liquid surface. Now, as you turn up that temperature, as you introduce more heat, the water molecules become more agitated. They start jiggling, bumping into each other, and more break free from the surface as water vapor. And then you increase that warming, continued warming, increases molecular activity so much that the air becomes saturated with water vapor. What I want you guys to remember is there comes a point where evaporation can no longer happen because the air is saturated. That means it's full of water vapor molecules. So in places that like the southeast United States, in these humid states, evaporation doesn't happen as much as in places that are dry. So if the air feels humid, there's not a lot of evaporation happening. Why? Because the air is saturated with water vapor molecules. Unlike here, it's a drier area, so more evaporation happens. So if you've ever been in a humid place, even if you've been to Cancun, right? It's hot outside and it's like your sweat doesn't dry off, you just stay humid. It's less forgiving than if you're in a very dry area and you're outside sweating. It's evaporating and you're cooling yourself off more efficiently. Rates of evaporation. Strictly speaking, water vapor is added to the air when the rate of evaporation exceeds rate of condensation. Okay? In other words, there is net evaporation. For evaporation to happen, first, obviously, you need temperature, right? Water molecules in warm water are more agitated than in cold water. So more evaporation happens from warm water, correct? Than cold. Think about the globe. Think about the latitudes. Where do you think we find the most warm water? Good, closer to the equator, right? In the tropics. Why? Because they get the most sunlight all year long, right? We learned about this. 0 degrees to 23, even 30 degrees north and south. That is that belt where you have the most evaporation or warm water happening all the time. Okay, good. Then you need water vapor content. Evaporation, like I mentioned, happens more rapidly when there's little water vapor in the air. So you need that wind to come in and move those water vapor molecules away, the ones that already have evaporated, so more evaporation can happen, okay? And then dew point temperature. Dew point temperature, temperature at which the air can no longer hold all of the water vapor, okay? This means that evaporation happens more rapidly when there's little water vapor in the air, and the rate of evaporation drops off as it gets closer to saturation. Another important word is evapotranspiration. Yes, evaporation happens over the oceans, but we also have evaporation happening off of plants, in the forest, in the rainforest, on the ground, anywhere that there is moisture, evaporation will happen, and we call that evapotranspiration. So a small amount of evaporation happens from land, soil, and plants. Good. Now let's move on, okay? So we did evaporation. You have all those water vapor molecules rising in the air. Now what's next? Condensation. Why do I have this picture here? Because I want you guys to think of back in the day when we were able to go and order a nice cold glass of a hazy IPA at your local watering hole. Back in the day when you were able to go somewhere, I haven't been to a restaurant since March 13th, so I'm kind of scared. But that's a whole nother subject. So think about a cup, right? If it's cold enough, my mouth's getting watery. If it's cold enough, there's beads outside, okay? So that's essentially what's happening in the atmosphere when we talk about clouds. So evaporation happened already, right? You had all those water vapor molecules rising up into the atmosphere. Now, what is going to act like that glass in the atmosphere? Because for condensation to happen, there needs to be a surface. There has to be a surface in order for that water vapor molecule to turn back into a bead of water. So think long back. Chapter 3. What is in the atmosphere that's just hanging out that can act as a surface? It's not a gas, okay? So water vapor molecules have evaporated, they rise, and they're looking for a surface. Are you saying aerosols and particulates? Is that what I hear? You're correct. Aerosols and particulates is the surface for these water vapor molecules. So now these water vapor molecules will rise up and they find that dust, ash, bacteria, pollen, smog, whatever, right? All those aerosols and particulates that we talked about, they find that and they grab onto it and then they turn into a little tiny bead of water. And that, my friends, is how a cloud is born. So when you look at a cloud, it's just thousands and millions of minute water droplets, and they make up a cloud. Pretty awesome, right? So instead of calling them particulates or aerosols, we are going to call them condensation nuclei. Miss, why do we need a whole new fancy word? I don't know why. It's science. Science just is fancy like that, okay? This is just a particulate or an aerosol. You guys know what they are already. If I asked you to name them and give me examples of them, you better be able to, because it was on the exam. It was on a quiz, right? Particulates, particles like dust, smoke, salt, pollen, bacteria, other compounds. In this case, we're just referring to it as condensation nuclei. That's it. It's just like a fancier term, okay? So as soon as temperatures cool to dew point, now that water vapor molecule grabs onto that surface and it begins to condense, and you have thousands of those, millions of those. Then you have a cloud in the sky. So then it rains, right? That's the next step. That easy. Once you have a cloud, it rains. No, it's a little more complicated than that. So I want you guys to take a look here. You have a typical condensation nuclei, a typical particulate is about 0.0002 millimeters. A large cloud molecule or droplet is 0.05 millimeters. And a typical cloud droplet is 0.02 millimeters. And a typical raindrop is 2 millimeters. Okay, so it's still, even if it's a cloud, how do those droplets turn into raindrops? That is what we're covering next. Next, we have precipitation. Okay, once we have that cloud 100% saturated, now what happens? How do those little cloud droplets come down to earth as rain? So that they cannot just fall to the earth as rain. There's something that's happening within those clouds to get those droplets to turn bigger. Okay, they have to get heavier in order to fall to the ground as rain. So turbulence, wind, keeps these little minute cloud droplets of water suspended in the atmosphere. In order for it to rain, there's two processes, okay? First process is the collision and coalescence of water droplets. This happens in what we call warm clouds. Warm like 78 degrees warm? No, warm like 0.01 degrees warm, or 1 degree warm. Sorry, I don't know why I said 0.0. Like 1 degree Celsius warm. That's relative to this process, okay? It doesn't mean it's warm. It just means that there's enough temperature or energy to get those molecules jiggling. So what happens when these molecules start to jiggle? They bump into each other. And what do we know about water? Is that water has adhesive, cohesive properties, right? If a water molecule bumps into another one, do they kind of do a bumper car thing? No, they're going to collide and get bigger. They stick to each other. So as those clouds, we call warm clouds, because they're at least a degree warm, 1 degree Celsius, that starts the movement of these water droplets. They bump into each other, they get bigger. And then what happens? They get bigger and bigger, and when they're heavy enough, they start to fall to the ground as rain. Okay? Collision and coalescence of water droplets. Some cloud temperatures are greater than 0 degrees Celsius, known as warm clouds. In these clouds, rain is produced by the collision of water droplets. Tiny droplets must collide into drops large enough to fall as rain. This is the process most responsible for precipitation in the tropics because that is where most warm clouds are found. Pretty cool, right? All this stuff. Now, next time it rains, maybe you guys will think about this class and be like, oh, wow, there's so much going on in the atmosphere. All right, second process is the ice crystal formation, also known as the Bergeron process. This happens in cool or cold clouds. Some clouds or parts of clouds are high enough to have temperatures well below freezing, known as cool or cold clouds, okay? So they have, instead of, because they're so cold, these water droplets, these like tiny minute water droplets, start to freeze. So when they freeze, they start to suck up the surrounding water droplets, okay? So they turn into a large ice crystal. So when that crystal gets large enough and heavy enough, it falls. Now it falls to the earth. It might start off as a ice crystal, but probably here in Los Angeles, we see it as rain. Does that make sense? Because once they start to fall, the lower portion of the atmosphere is warm enough to where it melts and we feel it as rain. Okay, so ice crystals grow by attracting water vapor to themselves, causing liquid water droplets to evaporate and replace lost water vapor. This process of ice crystals growing and clouds shrinking may keep going until the ice crystals are big and heavy enough to fall. Ice droplets may melt as they fall and become rain at the surface. Pretty easy, right? What do you guys think? So different forms of precipitation. We know rain, snow, sleet is small raindrops that freeze during descent and reach the ground as pellets. Glaze, that's freezing rain, so it comes down as rain, but once it touches its surface, it freezes, and so kind of, I guess, I think of a glazed donut. I don't know why, but I do, so kind of picture that. Hail is one of the most complicated forms of precipitation with a very complex origin. They consist of very large or small pellets or lumps of ice. So, not gonna go over that. Global distribution of precipitation. So, based on latitude, obviously, but other factors are involved. So this is just going to look at globally where are more rainy areas at. So if you think the tropics, you're absolutely correct because the tropics has that ITCZ, right? The constant band of clouds. You guys remember that from last week? That constant band of clouds. And so you're going to have constant rainfall. And then that's where you find your rainforests of the world. So it's not this big like coincidence. It's because at the equator, you get most sunlight all year long. And the equator is more water than it is land. So you're going to have a constant band of clouds, constant rainfall all the time. You're not really going to have a change in seasons there. It's pretty much the same all year long. How do we map this? So on these lines that join points of equal quantities of rainfall or precipitation, you draw a line on the earth and you connect equal areas of precipitation. We call that an isoyet. So here you have the darker blue is the most precipitation, and that yellowish color is going to be the driest areas. So you can already see similarities, right? In the tropics, all the rainfall, right? On the western portions of continents, here, dry, 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 dry. Why? Why is that? Well, because we have that constant high pressure here, high pressure here. You guys remember that? Subtropical highs, high pressure here, high pressure here. That's why, right? So that's why you're going to have dry areas on the western portions of these continents. And you also have very similar climate. So you have that Mediterranean climate zone here, 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 and here. You also have very, very good conditions to grow things like grapes. That's why we have awesome wine. I'm not a wine drinker, so I've heard from Napa Valley, Chile, South Africa, and Australia, obviously the Mediterranean basin too, right? Regions of high precipitation, 3 locations. Obviously, you have where the ITCZ is, you have those trade winds coming together and lifting up, forming those clouds, constant precipitation. Those tropical monsoon areas where the trade winds switch position, and then you have winds from over the ocean coming in overland, bringing in all that moisture, right? You remember those monsoons? And coastal areas where the westerlies lie. Regions of low precipitation, areas of the subtropical highs, Southern California, Chile area, South America area, Western Southern Australia, and Western Southern Australia and Western Southern Africa, right? Interiors of continents, because they don't have that proximity to the ocean, and high latitude regions, very, very high latitudes. Acid rain. So unfortunately, whatever's in the atmosphere comes down with rain. And it doesn't mean like acid, like our skin's going to fall off our body, right? We're going to melt. No, acid means that the water has become acidic, just like our oceans are becoming acidic. Now there's so much CO2 and junk in the atmosphere. When it rains, that rainfall is so acidic. Pollutants fall to the earth with either rain, snow, sleet, fog, and they do have damages to aquatic ecosystems. So when that rain falls and it runs off into our oceans, before it gets to our oceans, it gets into our rivers and lakes, these aquatic ecosystems start to suffer because now the water is too acidic. So any vegetation or life within these ecosystems will be threatened. Forest diebacks. This is a picture here of a dieback of a forest, specifically due to acid rain and damages to buildings and monuments. I don't care too much about that, but I mean, it could be harmful for ecotourism. And this is a picture of a building that has been damaged due to acid rain, especially if the building is historic. It can be quite sad. All right, you guys, that was a lot of fun. I will see you guys next week for chapter 7. And thank you for your time. And email me with any questions, okay, guys? And finish your module for the week. Have a great day.